All right. Today we'll talk about some of the basics of statistics. Actually, the ones which are very familiar. Okay, the mean, median, and the mode. Okay, we'll focus on mean and understand the differences. So, what is a? I mean, like statistics again, collection of data, analysis of data, representation of the data, okay, inference of the data. It's all around data. Suppose I have data like 4, 5, 6. This is one data source, and let's say it is created by source A, and another data source is like it creates like minus 40, 5, 50. Okay, this is from another source. Two processes are generating the data. Okay, if you go with okay, I wanted to find out. Um, let's take one more example before I go here. Suppose if you wanted to, represent the performance of the student. Okay, normally what we do is we take all the marks of the he has scored or he or she has scored. Okay, and average it with the total number of subjects, and the number you get is the representation of his performance. Okay, so suppose a student gets 75 percentage as his average, then which means that that is his benchmark, okay, averaging all his total marks of all the subjects. Suppose another student gets 80, that is the representation of, okay, he has fared a little better than him. So if someone gets like 68 or something, it's like they fared little less than this. So that's a kind of an indication or we can call it a summary of the overall data. Okay, that summary point is called a statistic. Okay, the mean, median, mode. I mean, these are all statistic. Okay, so any collection of data you can represent using a statistic that gives you an idea of about the performance of something. Okay. Similarly, if you take these two processes, okay, these are not marks; these are completely different random numbers. And if you go with an average, okay, let's say the mean, arithmetic mean. Here the mean is 5. Okay, like 6 plus 4, 10 plus 15 by 3. 15 by 3 is equal to 5. Here it is like 55, 55 minus 40 is like again 15. Total number of data is like 3 is equal to 5. So if you go with mean here, it gives you a good indication that it is a nice representation. Okay, the average mark of a student gives you a good indication of their performance. Okay, mostly because a good student normally performs well in most of the subjects. An average student normally performs average. Okay, there may be exceptions, outliers. One can perform well in one or other, but overall, okay, the perception and the way we kind of accept is, okay, a mean is or average is a good representation of the total marks and of the performance of the student. Okay, otherwise you will have to if someone asks what is your score, you will have to kind of tell all the marks, and it's difficult for somebody to kind of summarize what score it is, to kind of compare between two people. Okay, compare between the student A and B, compare between two classes how they performed. Okay, so mean is a kind of good estimate here. So in this situation, the mean was good, but in this situation, if you look at mean, and if you think that both these data sources are completely, are very similar because the mean is the same, then we may get fooled. Okay, that is where we wanted to think beyond mean. Okay, think beyond mean, and sometimes average, mean or average means the same. So it's sometimes not representative of the data. Okay, you may get misled if you try to go with the mean. So there are couple of things like these are like arithmetic mean and averages. If you go for the positional average or positional, based on position of the data, you want to take some guess of what is the representation, then we what we call it as median. Median is the center value. Here the median is 5. Here also the median is 5. Okay, and mode is the kind of repeating values. Here there is nothing repeating much, but still we can assume that the mode does not kind of represent the real data as well. Okay, here in this case as well. So mean is the average, median is the positional. If you sort it in the ascending order and find the position which is in the center, then that is the median. Okay, or if you go by frequency of number of repetitive frequencies, then you can use mode. Okay, for example, salaries, they use median salary because there will be outliers. One may be getting very low salary, one may be getting very high salary. Suppose we wanted to understand what is the salary range of a particular city or a particular company, Then the most number of repetitive salaries ranges helps us to find out what is the median salary. Okay, that helps us to find, that may be a good estimate of a central tendency. So ultimately, what we're trying to achieve here is trying to find the central tendency of the data, where the data lies in. Data is centered. Okay, here in this case, the data is centered around 80, 75, 68. As marks here, it is centered around 5. Okay, that's what we're trying to find out. So sometimes centers may not represent the real spread of the data or real meaning of the data. That is where we want to go beyond it. So even median or mode does not help here. So another important concept along with mean is the variance. Okay, variance. Okay, standard deviation is the square root of variance. Okay, if you find the standard deviation is the square root of the variance. So what it really is, you subtract the value. Okay, value x minus the mean, okay, and the whole square, and divided by the number of samples. Okay, here it is 3. Okay, so if it is population, assume that it is a population, you go with the n. If it is a sample mean, if it is x bar, which is the kind of a sample from a population, then you go by n minus 1. So if there are 3 values, you go by 3 minus 1. If there are 3 values here, you go by 3 minus 1. Okay, but we assume there is a population and we use this. So what it really means is that you have mean as 5, the value, I mean, like 4 minus 5 is minus 1, the whole square. Okay, this is summation actually. Summation of is equal to 1 to n, okay, the number of values. So minus 1 squared, then 5 minus 0, 0 squared, then 6 minus 5 is 1 squared. Okay, and divided by 3. Okay, so here it is like 1 plus 1, 2 by 3. 2 by 3 is the variance of this particular data. Let's check what the variance of this data is. Okay, it is again 40 minus 5, it's minus 45 the whole square. Okay, and then plus 5 minus 5 the whole square, it is 0 square, and then it's 50 minus 45, there's a 50 minus 5, that is 45. Okay, the whole square, again assume that's population, so it is like 3. Okay, so now the value comes around something like 2025 or something. I mean, let's not go with the actual numbers, but you see the variety of, or the variance of data, which means that the data is spread less here. Okay, and the data is spread a lot here. Okay, that's what it means actually. Here the spread of the data is less, here the spread of the data is large. Okay, that gives you a good indication whether the data is like this or data is like this. Okay, so these two are distributions. Okay, distributions from which this data is coming from, and let's say this is like 4, 5, 6 centered around this. Here it is like minus 40, 5, and here it is 50. So it means that the data is like spread out. So both are not equal. Both distributions are not equal. So that's the reason a mean may not be a good representation. We should also use variance along with this. Okay, and try to find out. If you take the square root of this, you get standard deviation. So it's again just a number to represent this. Okay, so. Okay, we have seen the mean, okay, and the variance of how it is useful to kind of understand the data between and the spread of the data, which with both together we will be able to tell something about the data, okay, and the process which led to the data. Now let's extend that idea of to a kind of 2 dimensions, where we have 2 sets of values, okay, where we have something like 3 points. Okay, let's take 1 point is here, and this is like, let's say this is 1, this is 1. This is minus 1, and this is like my x-axis. Okay, just trying to put it here. Okay. So if you take a point here, it is 1, 1. Okay. The point here, it is 0, 0. And if you take a point here, it is minus 1, minus 1. Now if when you have 2 dimensions like x and y, because normally data does not lie in, I mean, 1 dimension in real world. If you take an example of a house price prediction, you have dimensions like the square feet, number of bedrooms, okay, and the number of balconies and area, whatever, everything will be a dimension. And if you try to plot it, you will get multiple dimensions. If you are trying to find out the difference between 2 houses, whether they are same or not, you may have to deal with the means and variances, okay, in multi dimensions. So let's assume that this is a 2-dimensional data, okay, and we have a point like this. Now let's, in two-dimensional data, you'll have to calculate variance in both directions. So you'll have to, it's variance, this is the point here. So we need to find out the variance in x direction and the variance in y direction. So for all 3 points, we need to find out the variance of x and variance of y. Okay, let's find the variance of x. Okay, and variance of x is nothing but 1 x minus, the formula is x minus nu by n. This is the whole square, and summation of y is equal to 1 by n. This is the sum. Okay, and here the mean is the mean of x is like 1 plus 0 plus minus 1. Okay, that is like 0 by 0. The mean is 0 because this line, if you draw a straight line here, for 3 these points, this is the mean, and the mean is 0 here. Okay, so that's the reason here the nu is 0. So if you try to find the variance, it will be like 1 minus 0 the whole square, that is 1 square. Then the next point will be 0. We are trying to look at the x-axis. This is x, this is y. So we'll look at the x next. Okay, this is 0 square. Okay, and then this will be like minus 1 square. Okay, and if you look into the variance here, it will be like 1 square plus 1 square plus 0, that is like 1 plus 1, 2. And total number of points is 3. We are assuming that it is a population, so we'll keep it 3. The variance is 2 by 3. Now let's check the variance of y. Okay, the y is again the same with respect to y-axis. So if you see here, it will be like we'll start here. So 1 minus 0 is again 1 square plus 0 minus 0 is 0 square. Okay, and then minus 1 minus 1 minus 0 the whole square. Okay, it is like minus 1 the square. Okay, so again it is like there are 3 points here, and 3 so it's 3. Again 1 square plus 0 square, that's 1 plus 1, 2, 2 by 3. The variance is 2 by 3. Now this is the data point which we have seen, and we found out the variance in x and variance in y. Suppose we assume that there is one more line. Okay, this is a one data, and let's assume that there is one more data. This is from different sources, from source A. Okay, this is from source A. Let's take this is from source B. Different process generating this data, and if you see here, this is like 1 comma 1, this is 0 comma 0, and this is like 1 comma minus 1. Okay, x is 1, y is minus 1. These 3 points. So let's just put this line here. So let's try to calculate the variance of this point. Okay, variance of x. Okay, for these points. So x again. If the x-axis, this is x, this is y. So 1, again the mean is 0 because 1 plus 0 plus 1, that is this is like this is 1, y is minus 1. So the mean again is 0 here. Okay, and we will try to calculate the variance here. So here it is like 1 minus 0 the whole square is equal to 1 square plus 0 square. Okay, and 1 minus 0 the whole square, again it's 1 square. 3 points. Okay, the variance is 2 by 3. And we'll see the variance of y. Okay, variance of y. 1 minus 0 the whole square. Okay, then 0 minus 0 the whole square. Then minus 1 minus 0 the whole square. That is like minus 1 square by 3. Again it becomes 1 plus 1, 2, 2 by 3. So if you look at it, okay, the mean is the same, the variance is the same. Okay, so we have data source which generates data points like this with slope pointing this way, and the values are moving up like this. If you look at the data source B, it is generating data which is like moving with a negative slope like this. So which means if I expand this, the data will be like this, it will go like this. Now if you assume if we just use mean or median mode, whatever it is, it will be the same. If you try to use the variance, okay, and try to find out whether these two data sources are same, we'll end up with the conclusion that yeah, it is the same because both are having the same variance and the same mean, which is kind of not the case, right? If you see, it's completely different. Okay, the data sources are completely generating data which is behaving differently. So we exhausted the mean and variance options. So now in order to get and solve these options, okay, we need to go for another concept called covariance. Okay, covariance is covariance between x and y. How does x and y vary together? So how do you calculate this? It's a product of the coordinates. Okay, and in this, let's calculate it for this side first, on this line first, and then calculate for this line. Product of the coordinates is 1 plus 1 the whole square, okay, then 0 square, okay, that is 0, and 1 into minus 1 is like minus 1 the whole square, okay, then 1 square. And if you see, sorry, you don't have to square it, you just have to multiply it, okay, just a second. Yeah, we'll continue. Yeah, we should not square it. I think there is a mistake here. It's minus 1 here. So just do minus 1. Okay. So yeah, so what happens is if you try to multiply these two, this becomes minus 1. And if you try to these two, it is 0. These two is like again minus 1. So if you add these two, it becomes minus 2 by 3. Okay. The covariance of this line is minus 2 by 3. Similarly, we'll try to find the covariance of this line. Okay, covariance of x and y for this line, this pair of lines. So if you see here, if you try to multiply the coordinates, it will become minus 1 into minus 1 becomes 1, it becomes 0, and this becomes 1. Okay, total number of points is 3. Okay, so it becomes 2 by 3. So if you see here, this is minus 2 by 3 and this is plus 2 by 3. So the covariance of this line is minus 2 by 3, the covariance of this line is 2 by 3. So we were able to distinguish between these two by using covariance actually. So we were not able to distinguish between mean, we are not able to distinguish between variance, but we were able to distinguish between covariance. So that is where when we go with multi-dimensional data, okay, we start using covariance as well, which plays a major role to determine the distribution of the data as well as understanding the process which generated the data. So if you try to put all this into a matrix, it is represented by what we call it as a covariance matrix. So if you try to take one line at a time, so we'll take this line, we'll take this line, we put variance of x, then variance of y, okay, and covariance of xy, covariance of xy, and covariance of xy. Okay. So it's a diagonal matrix. So these two would square matrix, right? These two might most likely be the same. Okay, so variance of x, variance of y, it is like here it is variance of x is what, 2 by 3, variance of y is what, 2 by 3, and covariance of x and y is minus 2 by 3, and the covariance of y and x and y and x both will be the same. So this is the covariance matrix. So we have moved from single dimension to 2 dimensions, and we found the covariance matrix with variances and covariances. So this matrix is useful to kind of do a linear transformation like any other matrix. So if you wanted to move from a point from a domain to codomain, okay, you do linear transformations, and a matrix is multiplied by that particular point. Okay, it will transfer the point from one point to another. That is why that is how you kind of do dimensionality reduction by projecting the data from one point to another using this covariance matrix. Okay, it's used in principal component analysis. So that the fundamental idea comes from this actually. So we talked about mean, median, mode, okay, and variance, covariance, and standard deviation is just the square root of the variance. It's just another representation of variance without the square root, because everything is squared here. When you do it, if it's just a square root of it, it becomes standard deviation. Okay, so basically it just measures the spread of the data. Okay, this is very important when you deal with a lot of statistical analysis. Okay, thank you.